Hello everyone, welcome to another lecture of Microcontrollers with Lab. In this lecture, we are going to focus on the sequential logic or sequential circuits. We will go through the introduction to the sequential circuits, and then we'll see different types of sequential circuits, and at the end we will have a look at the storage elements, which are mainly the latches and then the flip-flops. In the first part, we will focus on latches, and then in the next part, we will see details regarding the flip-flops. So as an introduction to the sequential circuits, we could say that a sequential circuit is a combination of a combinational logic or a combinational circuit plus storage elements. So the sequential circuit contains storage elements which are latches or flip-flops, and you can see that they are, let's say, placed here. And then we have the combinational logic. As you can see that it is here. Yeah, the combinational logic is here, and they are connected to each other. The combinational logic provides signal to the storage elements, and the storage elements provide signal or input to the combinational logic. The combinational logic implements a multiple output switching function. Inputs to the combinational logic are signals from the outside. So these are the signals from the outside, and the outputs are signals to the outside. And we have the outputs here. So these are the signals that will go to the outside. And then we have the next state, which is, as you can see here, an output from the combinational logic, which is an input to the storage elements, and the state or present state is the output from the storage elements, and it is an input to the combinational logic. So in this way, the sequential circuit will be able to store some information. For the combinational logic here, we have the next state, which is again the output of combinational logic. It will be a function of the inputs to the system from the outside and the state, which is the current state indeed. So next state will be a function of the inputs and the current state. As for the output, we have two different options. For the first option, we have the output as a function of inputs and the states. In this case, we call the sequential circuit as the Mealy machine or Mealy system. And in the second case, the output is a function of only the states. So inputs don't have any direct effect, let's say, on the outputs. In this case, the sequential circuit is called to be of Moore type. So we have Mealy and Moore. Again, in the Mealy case, we have the output as a function of both inputs and the states. But for the Moore model, we have the function, or we have the output being a function of the state only. And for both cases, the next state is a function of the inputs and the current state. So the output function then will, the type of output function, whether it is Mealy or Moore, it will depend on the specifications and it will affect the design significantly, whether the output is a function of only the states or the states and the inputs at the same time. We can categorize sequential circuits into two main classes, the synchronous and the asynchronous. This categorization depends on the times at which the storage elements observe their inputs and they change their state. So if the storage elements, which are going to be latches and flip-flops, could receive the input at any time instant, and they can change their output or their state, indeed their value, the value which is stored in the storage elements could be changed at any time, then the system will be called as the asynchronous. But for the synchronous case, the behavior will be defined from the knowledge of its signals at discrete instances of time. So not at any time, but at discrete instances of time, the state of the system and the outputs could be updated or could be changed. So the storage elements in the case of synchronous sequential circuits or synchronous sequential logic, they observe the inputs and they can change state only in relation to a timing signal. And this timing signal will be mostly referred to as clock pulse. And it will come from a clock. We will see the details regarding clock pulse later, but I can just show you here that the clock pulse will have this form. So for the synchronous system, the states should be updated only at discrete time instances, only at these time instances. And in between, even if the inputs to the system change, the state of the system will remain unchanged. In this case, we have a synchronous system. On the other hand, for the asynchronous systems, the state of the system could be changed at any time instance. So in this case, the operation doesn't depend on the clock or clock pulses. So here for the asynchronous case, the behavior defined from knowledge of inputs at any time instant and the order in continuous time in which the inputs change. So if the inputs change at any time, then it will affect the state of the system, it will affect the output of the system at that time. Of course, keeping in mind that there are some delays in the gates, and since we are using the gates, there will be delays, and therefore the state and output will change after a given amount of time. But the operation of the system doesn't depend on the clock, and we don't have our system changing its states and at specific time instance. If we use the clock, or if we consider the clock as another input to the system, then an asynchronous, we can say that a synchronous system could be considered as an asynchronous system. So if we say that here we have a synchronous system which receives inputs and it also receives clock, which is in the form of a square waveform, then if we look at the clock as a separate input to the system, we can say that the whole system now could be considered as asynchronous one. However, the synchronous abstraction will make complex systems being tractable to design. So this will be beneficial for us if we have a system which could be considered as a synchronous one. The design will become easier. Okay, now let's see some details regarding the storage elements. First, we start with the latches, and we start with kind of simplest latch which is possible. The first one to consider is the basic NOR SR latch. So basically we have two NOR gates and their outputs are interconnected to each other. So the output of the first one is connected to the input of the second one and vice versa. And we also have two inputs to the latch, the R input and the S input. As the output, we take the outputs from the NOR gates. So they are called as Q and not Q. This latch is called as as an SR latch. So it's basic NOR SR latch. And we will see now how it operates. The sequence of the operation or the behavior of the latch is going to be considered. So we can also refer to it as this. We will have the R input, S input, Q output, and Q bar output, and this will be the SR latch. So let's see how we are going to, how the latch is going to behave. Yeah? Since we have two inputs to the latch, R and S, there will be four possible options for them to take in terms of the value 0, 0, 0, 1, 1, 0, and 1, 1. And now we can consider each of them one by one. So let's first focus on this case. When we have 0 and 1 as the input, let me show it maybe here. We have 0 for R and 1 for S. Let us see what we will have as the output values for Q and not Q. So since 1 is the input to the second NOR here, we can see that its output will be equal to 0 regardless of the value of the Q. So whatever value we had for Q from in the past, if we apply 1 to the S input, the output of the NOR gate here will become 0. And once the output of the NOR, the second NOR here, becomes 0, it is used as the second input to the first NOR, which has the 0 as one of the inputs. And now both inputs are equal to 0, and as a result, the output from that NOR gate will be equal to 1. And now 1 will be here, 1 and 1 will give us 0 as the output of the NOR, and the system will be stable as you can see over here. So therefore, when this is the case, when 1 and 0, when 0 for R and 1 for S, when we have this case, the value that we have for Q will be equal to 1, and the value that we have for not Q will be equal to 0. Now we can consider the next case. For the next case, let's consider this one. So 1 for R and 0 for S. Let me switch to the corresponding slide. So here, we have 1 for R, as you can see here, and 0 for S. And in the past, we had some value for Q and Q bar, but we will see that this time it doesn't matter whatever value we had. So as one input to the first NOR here is equal to 1, regardless of the value that we have here, the output will be equal to 0. Then for the second NOR, we have a 0 coming from the first NOR and a 0 coming from S, and as a result, the output will be equal to 1. Then this 1 will be provided as the input to the first NOR gate, and again here you can see that the output of the NOR gates will remain as 0 and 1 all the time, and that's what we have here. So now you can see that if we provide 0 for R and 1 for S, the main output Q will be equal to 1. If we provide 1 for R and 0 for S, the main output will be equal to 0. So that's why we can say that in the first case we are setting the latch, the output becomes equal to 1, and in the second case we are resetting the latch as the output becomes equal to 0. Okay, now we need to see what happens when we provide 0, 0, 0 for the inputs or 1 and 1 for the inputs. First, let's consider 0, 0. So let me maybe show it here. Draw and show it here. We have R here, S here, Q, and not Q. And now we are going to apply 0 and 0 here. So initially we had Q at the output of the first NOR gate. So here we have Q and we have not Q here. The result of the NOR operation here, for the first NOR gate, we have 0 NOR Q bar. So 0 Q bar OR. We know that 0 Q bar OR will give us not Q, which is indeed equal to Q. So the output will be equal to Q. And if we consider that for the second NOR gate here, the output from the NOR gate will be equal to Q bar, as it was before. So as long as we provide 0 and 0 as the input to the latch for our SR latch, you can see that the outputs will remain the same. So we will have Q and not Q here. The state of the latch will remain the same. So it will hold previous value. And now let's see what happens when we provide 1 and 1 for the latch as the input. So let me draw it again here. We have R, S, Q, not Q. If you use 1 here and 1 here, as one input to the NOR gate is equal to 1 for the first one, its output will be equal to 0. And similarly for the second one, it will be also equal to 0, regardless of the value that we have for Q and Q bar from the past. Yeah? And therefore, both Q and Q bar will be equal to 0. And this is the case which is not designed for us, because we want to have Q and Q bar being complement of each other. They cannot be both equal to 0 at the same time, or they cannot be equal to 1. So this is a case which is not valid, or it is a bad case. We are not going to use it. So for the SR latch, this is the case that we will not, we try to avoid it. Yeah, we avoid this case. But the other three are the ones that we are going to use. If you want to set the latch, you provide 0 and 1 for R and S. If you want to reset it, you provide 1 and 0, and otherwise you provide 0, 0, such that the latch keeps or holds its previous value. Another type of the latch that we can consider is called the basic NAND, not S, not R latch. So you can see that the structure is quite similar, but in this case we are using the NAND gates instead of the NOR gates that we had in the previous case. The output of one NAND gate is the input to the other one, and vice versa. If we look at the kind of truth table or the function table for this latch, for not S not R latch, you can see what happens. If we have 0 and 1 for not R and not S, we will have the output, the main output, being equal to 0, and we are having the reset case. So you can see that not R is equal to 0 and not S is equal to 1. Alternatively, we can say that R is equal to 1 and S is equal to 0, similar to what we had in the previous latch. So in this case, we will have resetting. If we provide 1 and 0 for not R and not S, we will have the set case. The output will become equal to 1. If both of the inputs are equal to 1, not R and not S, we will have the hold previous value case. Q will be equal to Q, not Q will be equal to not Q. And finally, this case, when both not S and not R are equal to 0, will be a case in which both of the outputs will be equal to 1, and it's a case that we will try to avoid. So this indeed is kind of trying to set the latch and reset this latch at the same time, and obviously we cannot do that. You cannot set the latch and reset the latch at the same time. So it's the case that we will avoid in it. Alright, so those latches that we have seen till now, the SR or the not S not R latches, they didn't have clock input. So they were basically asynchronous. Now we are going to introduce the clock to our latches, and we will have a clocked SR latch. You can see here that two additional NAND gates are used. They receive the S and R input, and we have a third input, which is the clock or C input. So in this case, we will have a clocked SR latch, which is constructed using the NAND gates. In terms of the time sequence, its behavior will be similar to the basic SR latch. So with S and R, so in this case, indeed, S equal to 1, R equal to 0 will set, or the Q will be equal to 1. With S equal to 0, R equal to 1, we will have reset. Q will be equal to 0. With both S and R equal to 0, we will hold, the latch will hold the previous value. And with S equal to 1 and R equal to 1, we will have the case which we need to avoid. So this will be in an invalid combination of the values for the inputs. But now the S and R inputs are only observed when the C is high. C here is the control or clock. You can see that I can show it to you here. Yeah, if we set C equal to 0, if C becomes equal to 0, as the output of the NAND gate here, we will have 1 at the output, and here we will have 1 at the output of the NAND gate. So when C is equal to 0, this will be the case. Here we have Q NAND 1, so Q and 1 will be equal to Q, NAND will give us not Q, and here we have not Q NAND 1, which will give us Q. And as a result, you can see that when C is equal to 0, the system will hold its previous value. And if you change the value for S and R, there will be no consequences, nothing will happen. But then if we make C equal to 1, let me show that as well. If we set C equal to 1, let's see what we have at the output of the first NAND gates. Here we will have 1 NAND S, we will have not S, and here we will have not R. And depending now on the value that you provide for S and R, we'll have value for not S and not R, and therefore we'll have the proper operation from the latch. So when C is equal to 1, if you change the value for S and R, then the latch will behave accordingly. Now, as I already mentioned, here we have some invalid combination of the values for the inputs that we need to avoid. But if you want to avoid it, let's say systematically, we can make a connection between S and R by placing an inverter in between them. But in that case, we will have a latch which is not called as SR latch anymore, but this time it will be called as the D latch. You can assume that here we had S and R. So similar to the SR latch, the clocked SR latch here. But now there is a relation between S and R. You can see that R is equal to not S. So the case of 1, 1 will never happen. So an inverter is added to the SR latch, and it gives us now the D latch. Let's see how the D latch is behaving. So now, as I mentioned, we don't have the indeterminate state. We will not have the case in which both S and R are equal to 1, and we want to set the latch and reset the latch at the same time. So let's see what happens. When C is equal to 0, there will be no change. So again, we have the clocked latch here. With C equal to 0, nothing happens. But when C is equal to 1, then depending on the value of D, whether it's equal to 0 or it's equal to 1, we will have the reset state, and or we will have the set state. The Q will be equal to 0 or Q will be equal to 1. So keep in mind here the relation between D and Q. So when D is equal to 0, Q is equal to 0, and when D is equal to 1, Q is equal to 1. So basically Q here, or the state of the latch, is following the input, which is D. So this is the clocked D latch for us. And we will see how this kind of latches could be used in order to design the sequential circuits. Okay, so I think that's all for this part of the lecture. In the next part, we will talk about the flip-flops. I hope you have learned the main concepts regarding the sequential circuits, how the latches are constructed using the NAND gates or NOR gates with the interconnections between them. And you also have learned about the SR, not S, not R, and the D-type latches, and how we can introduce the clock into our latches. Thank you for watching and see you in the next part of the video soon. Bye for now.